Okay, now we move on to another kind of force due to a magnetic field or interaction between two magnetic fields. But here you don't have a current or a conductor carrying a current. Here I'm pointing out that there is a magnetic field pointing into the page. So you have a magnetic field into page. I can create that by placing a north pole above the page and the south pole behind the page, so the field will be pointing inwards. So what happens if you have a charge, a positive charged object, moving to the right and entering the magnetic field? In this case, if you have a moving charge, you have a current. And if it's a positive charge, then the current is in the same direction as the motion of the particle. If you apply Fleming's left-hand rule here, if you have a field which is pointing inwards into the page and the current to the right, you'll find that the thumb is pointing upwards. This leads to the conclusion that this positive charge will experience a force upwards as it enters the magnetic field. So it will curve up. Since the velocity vector is perpendicular to the force vector, then you will move in a curve. But as soon as you leave the magnetic field, you'll start experiencing no force and continue in the straight line. So if you have a positive charge entering a magnetic field, you can find the direction of the deflection of this charge by using the Fleming's left-hand rule. So moving this to the side, we will see what happens if you monitor a negative charge entering the magnetic field. So for a negative charge entering magnetic field, if the charge is moving to the right, then the current is defined to be in opposite direction to the motion of the negative charge, so the current is to the left. So this charge will experience an opposite force since it's experiencing an opposite current. So this means that this charge will be moving downwards in a curve until it's exiting the field, then it moves in a straight line. We can see this by using the Fleming's left-hand rule here. So the field is pointing into the page and the current, now the field is pointing into the page and there is a current to the left. The thumb is pointing downwards. That's why the negative charge will experience a downward force, and it's also perpendicular to the vector of the velocity, so it will curve downwards as it goes through the magnetic field. So one of the questions you're asked about this is how to calculate the force on this charge. So basically, we remember that the force is equal to Bill sine theta. But here, the magnetic field is always perpendicular to the direction of the motion. So either you're moving right, left, up or down, or inclined direction, you will still have the magnetic field pointing upward into the page. So it's always perpendicular to the current. So you don't need sine theta because it's equal to 1. So now we have a problem. You don't have a magnitude for the current, and you don't have a wire with a certain length. So we use the definition of current to solve this problem. The definition of current is the rate of flow of charge. So basically you have a charge per unit time multiplied by the length. But just pay attention to this part. If you have a length divided by time, that gives you distance over time, which is speed, or displacement over time, which is velocity. So you can just calculate the force by multiplying the flux density of the magnetic field by the charge of the moving particle by the velocity of the moving particle. So you have flux density in Tesla, you have charge in coulombs, and the speed in meters per second. to get the force on the charge in newtons. So basically, this is how you calculate the force on a moving charge inside a magnetic field. Okay, another question that you may be asked is define the shape of the path of the charged particle inside the magnetic field. You will find that this path inside the magnetic field, for example, from this section to that section, is a part of a circle. Why? Because the angle between the force and the velocity vector is always 90 degrees. So if the force is always perpendicular to the velocity, you'll find that these forces always converge towards a central point, which is the center of the curvature. So it's a centripetal force. So what can he ask about in this case? We now establish that it is a circular path because the force is always perpendicular to the velocity. But he can say, can you calculate the radius of this circular path? Or if you have the radius, can you calculate the charge of this moving particle? Yes, you can. You can just equate the centripetal force with the magnetic force. So the centripetal force is equal to mv squared over r. And the magnetic force is equal to bq v. So you can cancel out the square with the v. So if you know the flux density and you know the mass of the particle and you can measure the radius of curvature, you can simply calculate the charge. Or if you already know the charge, for example, it's an electron or something, you can easily find the mass of the particle. And this is, by the way, how to find out the mass of an electron. So in AS, we took that you can calculate or approximate the value of the elementary charge, which is a charge of 1 electron, by using an oil droplet suspended in an electric field and equating the weight with the electric force. So if you have two plates and an oil droplet here, which is charged, if you charge the upper plate positively and the lower plate negatively, and this droplet is negatively charged, you can say that the upper force, which is equal to EQ, where E is an electric field strength, and the downward force is equal to mg, then you can get numerous values for Q, which is the charge on the oil droplet, and it's a negative charge. If you use the least common multiple method, you can easily calculate the charge of 1 electron, since the charge is always a multiple of the charge of 1 electron. Now, if you know the charge of 1 electron and you can use this equation, if mv over r is equal to bq, you can find something called the specific charge, which is the ratio between charge and mass. So a specific charge will be equal to v over br. So if you want to measure the radius of the rotation of an electron inside a magnetic field, you can fill this region with a low pressured gas. So when the electron accelerates due to change in direction, it ionizes the gas and causes it to glow, creating a light, much like the lightsaber of Star Wars. So you can actually measure the radius of the circle. And if you already know the flux density of the magnetic field, so you have everything that you have. If you already know also the speed of the electron as it enters the magnetic field, then you calculate something called the specific charge, which is a charge per unit mass. But you already know the charge from the Millikan's experiment here, so you can easily calculate the mass. So basically, for any circular motion inside the magnetic field, you can just solve the problem by equating centripetal force and magnetic force, which is equal to BQV. Okay, let's move on to the next part. We mentioned before that to calculate the specific charge, you need to know the speed, the flux density, and the radius. These two values are easily measured using a hole probe and a ruler, But how can you calculate the speed or measure the speed of an electron? There is a device called the Velocity Selector. Basically, if you emit a number of electrons, not all of the electrons have the same speed. So basically, you have a range of speeds. So you cannot know the velocity of one electron entering a magnetic field. But if you place a magnetic field, which is into the page here, so here you have a magnetic field into page, and in the same region you apply an electric field with strength E. Here the electric field is downwards, and the electron should feel an upward force due to the electric field, and using the Fleming's left-hand rule, it should experience a downward force due to the magnetic field. So, which electrons will pass through undeflected? Passing through undeflected means that these two forces are equal and opposite in direction. So, basically, you should equate the electric force to the magnetic force. So, how can you calculate the electric force? It's the field strength multiplied by the charge. And how can you calculate the magnetic force? It's B Q V. You'll find that Q does not affect this equation, or the charge that is independent. So this equation is independent of charge. If you place your equation now, so it's E is equal to B V, then the velocity of the electrons which pass through the magnetic field undeflected is equal to E over V. And you can easily calculate the field strength using V over D, where V is a potential difference across the plates here. So you can place a positive voltage here on the upper plate, and you can earth the lower plate, causing a potential difference of V, and the distance D is the distance between the two plates. So you can easily calculate the the electric field strength, and you can easily measure the flux density using a device called the Hole probe. If you want a certain velocity, you can make sure that the velocity is equal to this ratio. You can manipulate this ratio or the speed selected by manipulating the voltage and the distance between the plates, causing the electric field. So this is another question that you may encounter. An electron moving through two fields, one magnetic and one electric, without any deflection. But with an electric field, it would deflect upwards. With a magnetic field, it would deflect downwards. In this case, you can always find the direction of the deflection using the Fleming's left-hand rule. So whenever you're asked about this velocity selection, or just an electron not deviated due to two fields, electric and magnetic, you can just equate the two types of forces here, reaching this conclusion. Okay. We mentioned that we can measure the magnetic flux density using a device called a Hole probe, which uses something called the Hall effect. So basically, if you have a metal strip and you pass a current through this strip, so basically this is the direction of the electrons moving into the metal strip from the left side and going out of the strip from this side. So you have a current in this direction. The current is always defined as in opposite direction to the direction of the electron flow. So basically, if you place this metal strip inside the magnetic field of a magnet or a coil or a solenoid or anything like that, and you place a probe at right angles to the field, the electrons moving through the strip will experience a force. If you apply Fleming's left-hand rule, so we can take this picture and magnify it. Now, the field here is pointing downwards, down the page, and the current is to the left, you'll find that the thumb is pointing out of the page, which means that these electrons will be accumulated on this side here. So this side will become negatively charged, leaving the other side positively charged. So you will find that the faces parallel to the current having a potential difference. If you measure this potential difference using a voltmeter, you will find that the more electrons accumulating on this side, the greater the voltage becomes, the greater the hole voltage becomes. This is the idea of a hole probe, that you create a potential difference parallel to the current, in two plates parallel to the current. But this voltage has a maximum value, since creating two plates with opposite charges creates an electric field. So basically you have a magnetic field and electric field. The greater the strength of this electric field will cause an electron in the middle to be attracted to the other side towards the positive charge. So basically you have two forces, a magnetic force and an electric force. When does this voltage stop rising? We call it the hole voltage or the hold voltage. It's when the magnetic force is equal to the electric force. Okay. First, let's give dimensions to this metal strip. If it has a cross-sectional area called A, and this here is the thickness of the strip, we will call it T, and this is the width of the strip, we will call it W, and this is the length of the strip, we'll call it L. So, using this method, the electric force is equal to V, the hole voltage, over D, which is the distance between the two sides, this side and that side. So the distance between them is W. So it's V over W. That's the field strength multiplied by the charge, EQ. And it's equal to the magnetic field, which is equal to BQV. You'll find that this is independent of charge. You lose the charge here. And furthermore, you may remember from your AS exams, there was an equation said that the current inside any conductor is equal to NAVE, where N is the number of charge carriers or electrons per unit volume. And A is the cross-sectional area. V was called the drift velocity. And E is the charge of one electron, elementary charge. So you can replace V here with I over NAE. So P multiplied by I over NAE is equal to the whole voltage over W. But the area here is equal to W by T. This area is equal to the width of the strip multiplied by the thickness of the strip. So you can rewrite this equation as BI over NWTE equal to the whole voltage over W. You'll find that W is cancelled out. So you get here that the whole voltage measured by the voltmeter across the strip is equal to BI over NTE, where N is the number of electrons per unit volume for this type of metal, T is the thickness of the metal strip, E is the charge of one electron, and the current I is equal to the current through the strip. So if you keep the current constant, then all this part is a constant. So the whole voltage is proportional to the flux density. So you can simply calibrate the voltmeter, not to read voltage, but to read flux density in Tesla. So this is how you use a whole probe. So this concludes the types of questions that you may be asked about in a final exam about magnetic fields. So let's go over what we discussed. You can either be asked about directions of magnetic fields or the shapes of a magnetic field around a straight wire or a solenoid. You can do this by using the right-hand grip rule, or you can be asked about the direction of a current and force on a conductor in a magnetic field, and you can find that using the Fleming's left-hand rule, or can be asked to calculate the force on a conductor inside a magnetic field using Bill sine theta. You can be asked about the definition of flux density or the unit Tesla using the equation Bill sine theta. You can be asked about using a balance to measure the current. So basically the change in the force is equal to the magnetic force. You can be asked about two wires carrying current in opposite directions or in parallel, same direction. So same direction, attractive force, opposite direction, repulsive force, and the force is proportional to the current's length and inversely proportional to the separation between the wires. A moving particle will also experience a force which is equal to BQV, and it moves in a circular path since the force is always perpendicular to the direction of the velocity, and you can solve any question about that using the equation between the centripetal force and the magnetic force, which leads us to the specific charge here, which is Q over M, charge over mass. Or you can be asked about an electron or a charged particle not deviating between inside two magnetic fields, electric and magnetic, and you can equate the electric force with the magnetic force, resulting in a velocity selection equation, which is E over B, or the Hall effect, which causes a voltage across two areas which are parallel to the direction of the current due to a magnetic field placed at right angles to the probe. And by the way, if the angle changes and the strip becomes parallel to the probe, then the whole voltage becomes 0. And if you increase the angle, the voltage increases until it becomes 90. Here also you equate the two forces, magnetic force and electric force, and you use this equation for the drift velocity. So this concludes this video about magnetic fields and all the questions that you may encounter in the final exam about magnetic field. Thank you and see you in the next video.